Hello, so today we are doing this problem called Permutation 2, which is very similar to a problem I did before called Permutations, problem 46. I will put the link in the description for the solution for that one. I think you should watch that one first. And this problem says that we get a collection of numbers that may contain duplicates and want to return all unique permutations. So for example, with these numbers, we can have 1, 1, 2. So you can see here 1 and 1 are duplicates, contrary to the previous problem where the permutation problem where we had that it's a collection of distinct integers. But here we may have duplicate integers and want to return all the possible unique permutations. So we don't want to repeat the same permutation twice, because that may happen if we use the same method as the previous permutation that assumed that we had in distinct integers. So here the permutations for 1, 1, 2 are 1, 1, 2, 1, 2, 1, and 2, 1, 1. And so we want to generate all the permutations, but only the unique ones. Okay, so let's see how we can do this problem. So to solve this problem, permutations with the numbers being duplicates, let's first just revisit the template that we have for solving backtracking problems. So I will post the link anyway for the guide of a template to solve all or most, at least most backtracking problems. And so right now what we are going to see is, I'm just going to quickly go through it, which is the way to do that. It was that we just need to model the solution as a vector of partial solutions, and at each step we need to find the candidates that can extend that vector solution, and then we will check at each iteration if we found a solution. If we did, we want to process it and add it maybe to a result list or print it or anything we want. And so the template was that first we check if we have a solution, then we process it, we add it to a list of results or something. Otherwise, that means we don't have a full solution yet, and so we are going to look and say, okay, at this step, what could be my possible next steps? And then we are going to get all of them and go through each one of them one by one, which is this candidate, and take each candidate and add it to the partial solution, which is A, and then do a move, make a move, and then backtrack to the next position in the partial solution A, and then make the move. And that's pretty much it. And so we need to find these templates. And if you remember, if we look at this, the way I solved the initial permutation problem, which is not the one with duplicates, I will also post a video of the solution for this one in the description. But for this problem, which is very similar, the only difference is that in the new problem we have duplicates. We generated a vector solution, which was that we put the element that we picked so far in the permutation. And so we said that at each position of the partial solution, our next step would be to pick any element that we shouldn't pick again. So to pick any element that we haven't picked yet, right? Because that is a possible element. Because if we picked an element before, we don't want to repeat it, so we didn't pick it. And so you can see here, if we picked an element before, we don't pick it again. So that's a problem here, because here we have duplicates. And so here we can have 1, 1, 2. And so if we pick one, we still can, we can still pick one. But with this, with our construction of candidates in this problem, we can't do that anymore in the new problem. And so, but everything else is the same. We find the solution when the length of our partial solution becomes equal to n, which is the length of the permutation that we are looking for. And processing the solution is just adding to some output array or output list. And then to make a move, we will need to append to the solution vector, and making we will need to still pop from the solution vector because we want to go back and add more to the solution vector. And so these ones we need to keep. We need to keep this one, we need to keep this one, but we need to change this one a little bit because we can't just pick any element not picked yet because we have duplicates. And so how can we change that? So that's what we need to change to make this solution, to solve this problem. And so one thing we know is that we can have duplicates. And so if we have duplicates like this, we don't know how many. So what we can do is just have a counter of how many of ones we have, right? So for 1 we have 3 ones, right? So if we have this, what we can do is, so what we had before in the construct candidate was without the duplicates. What we did before was pick any element not picked yet. But since now we have the possibility that the element exists multiple times, what we can do is change this to pick any element, right, that for which the counter is not 0, right? Because so that means that we will pick 1 and then decrement the counter, and the counter becomes 2. Then we pick 1 again, decrement the counter becomes 1, and then when we decrement it again, we can pick another one, but after that we have to stop. We can't pick it anymore because now the value is 0, right? And so the change we are going to do is that we are going to need to, for construct candidates here, we can basically go for all the element in the counter, which would be just the keys, which would be just the elements in the array. Any value in V that has the counter value bigger than 0, that's a candidate. Right? Because if the value is 0, that means we already picked all the elements available, and so we shouldn't pick it again, right? Because there is no other occurrence, right? And so to do that, though, to be able to decrement, we need to decrement here, right? So in our make a move function from the template, we'll need to change that a little bit. So the make move and make move will need to change a little bit. So before, make move was just appending to A the value V, and in the make we just popped V, right? And so what we need to do is decrement the counter now, because we have duplicates and we want to count so that when it reaches 0 we no longer include it in the candidates. And so what we need to do for that is decrement the counter by 1. And now since we decrement the counter, if we roll back and backtrack to this one, that means now we can pick this one, right? And so we need to, in the make move, we need to undo the operation that we want to do. So this is something to always keep in mind. Whatever operations we did in the make move, we should undo them in the make move. And so now that we have the construct candidate, we have the new make move and make move, and the other methods, which are is solution and process solutions, we have the same as the previous problem permutation. We can just use all the combination of these and solve the problem. And so let's do that then. What I need to do here is the template of backtracking, which was we will need to check if k is equal to n, this is basically that we have a solution. Then we need to process the solution, right? Which means just take the output array and append the partial solution that we have so far. And since k equal to n, that means we have a full partial solution now. And then after that, so this is process solution step. And now, so you can notice that I'm no longer putting them in functions, because now that we know the algorithm, we can, in the template, we can just apply it in line without needing to write in functions and then inline it again. And now we can just do else. We are going to go through the values in the counter, And what I will do here is, before executing this function, I would have counter that will just contain compute. I will show you how to easily do that in Python, but it just computes the count of occurrences of each number in the list of numbers, right? So this is just says for this one basically something like this. It says that it's a counter that says that 1 occurs 2 times, 2 occurs 3 times, and 3 occurs 1 time. So this is what I want this function to return to me. And now for constructing the candidates, I go through the elements in the counter, and then I check if the counter is bigger than 0. That means this is a candidate. And so this portion here for me is construct candidate function. The next step is to do the make move and make move. So the make move, as we said, is just these values here, and so I can just put them here, which is a append v, and then we need to decrement the counter because we used one value, and then we need to call the backtrack function, which is this whole function here. So this is just backtrack with the partial solution we have so far and going to the next index, which is k plus 1. And then we need to undo or unmake the move, which was just pop the element that we last added to a, and then increment the counter to undo this step here. So that would be counter v plus 1. And that's pretty much it. At the end, we can just return this output here. So you can see we applied the template, we just changed it the way we are doing construct candidate. Before we were just checking if the value is already in the partial solution, but now we are checking the counter because we have duplicates, and still applying the same template. Okay, so that's it for this explanation. I'm going to code this up now and see if it passes the test cases. Okay, so now let's code this solution. So first, checking if it's a solution. First, let's just define the backtrack function that we will pass to the partial solution and the index of where we are, and then we will call that here. And the partial solution starts out empty, the index starts out 0, and we need the output or the result list, where we'll put all permutations, and then we will need to return that. And so the backtrack function first check if it's a solution, and that means basically that this is equal to the length of nims. That means we have a solution, we have a full permutation, and so we can process it, and processing the solution is just adding the partial solution, which by now complete because k is equal to the length here. So that's A. Otherwise, we need to construct the candidates, and so we need the counter to keep track of how many we have still not used in the permutation. And so the function that does what I said, which was the for each element, putting each element as the key and the number of its occurrence as values. In Python, there is a method that does that, which is called just counter. So we are going to import that from collections, and then we can just use it here, counter of nims. And now we can just say if the counter is still not 0, which means there are still values we can pick, then we are going to make the move, which is appending to the partial solution first, and then decreasing the counter occurrence here, and then say backtrack to the next step, which is k plus 1. And after that, we need to unmake move, which means pop and counter increase by 1. And then that's pretty much it. The only thing we need to be careful of here is to copy it, because otherwise it will get modified again, and we will modify all the previous ones that we added to the list. And that's pretty much it. So let's run this. Okay, so this looks good. Another thing we can do here is we don't actually need this k value because we already have a list here that has the value, so we can just check the length of a, and instead here we don't need this k because we have a where the last index is just k, and we don't need this k here, and we don't need this 0 here. So let's just run this and submit. Okay, so this passes, yeah, so basically this is the isSolution method, this is the process solution, this is constructing the candidates, this is making the move, and this is backtracking, and this is making the move, and that's pretty much it. I will try to solve this with another method next. Okay, so let's implement the BFS solution for this problem. And so first we have the initial level, which is empty, right? And then we are going through each element and determine the permutations that include it, basically. So this is basically the permutations at position k, which let's call it I here. And so this is, let's call it maybe k, so that this becomes clear. So this is pk, pretty much. So we are going to generate the permutations at position k, and to do that we are going to, so these are the permutations at level pk. So new res is, actually let me just call it pk for this to be super clear. So these are the permutation at the current level, which is k, and then we are going to take all the permutations in the previous level, which are k minus 1, which are currently in res, and then we are going to go through each possible position, right, and insert in it, which is here we want to stop when we encounter the element, basically because if the elements are identical, we want to insert it just before it and not after it, because if we insert before it and after it, we'll end up with 1 1 and 1 1, right? And so what we are going to do here is, to do that, is just basically this here would just say stop when you encounter the element, don't add at that position. And so take the index at num plus 1. And the reason we are adding this here is because if there is no occurrence of the number, we don't want to have this index return minus 1 and have this be 0, and then basically not insert at any position, because range will stop, if it's range 0, it will stop at minus 1. Well, basically it won't stop at minus 1, it will start from 0 but not get to 0 because it stops at 0. And so we want to add this one, so at least if the element doesn't exist in the previous level, we can insert insert it, like, at least, because let's say with empty, if we start with the value 1, it's not in this previous res, right, because it's empty. And so if we don't do this add num, it would be minus 1 plus 1, and we won't enter even into this loop, right? And so this protects us from the duplicate case and does work with the case where it's not a duplicate. And then we will just add to the new set of permutations at this level, which are just inserting at position j, which means just doing something like this. Before j, the list before j, and then add the number, and then continue the list after j, at j basically. And then pk becomes, so pk minus 1 becomes the count pk, because we are going to increment k, right? And then we are going to return res. So it's not previous res, it's this one, the previous permutation. Seems there is a slight problem. Yep, so basically this is res actually, because that's what we want to return at the end. And pk minus 1 will go through all those in pk, all those in pk minus 1 permutation. This is where it is, permutation. pk minus 1 is the entire list in res, and then each permutation of that previous level is each element of each list in the list of lists result here. So what's this? Okay, so this passes. So to understand this a lot better, I think please watch the video in description for the problem 46, permutations without duplicates, and then watch this after that. I think that will be more clear. And thanks for watching, and see you next time. Bye.